Welcome back, my dear students. In this session, let us learn chapter number 10, Visualizing Solid Shapes. Exercise 10.2 is drawing and coloring, so let's skip this. Now, let us discuss about face, edge and vertices of a solid figure. So this is a cuboid. Here, this flat face are called face. This is face, 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 and this is face. So in this cuboid there are 6 faces are there, and this is edge, this is edge, this is edge. The joining point of the edge is called vertex. So this is vertex, this also vertex, this also vertex, and this is also vertex, and this also vertex, this also vertex, this is also vertex, this is also vertex. And these are edge, this is edge, this is edge, this is edge, this is edge. Now let us study about polyhedrons. Each of this figure, and this figure, and this figure is made up of polygonal regions which are called its face. This face meet at edge, which are line segments, and the edge meet at vertices, which are points. Such solids are called polyhedrons. These are called polyhedrons. Here, these shapes are polyhedron, and these are not polyhedron, as the face is not a polygon. Here, the face is not polygon. Here, for these shapes, its face are polygon, so that's why these are called polyhedron, and these are not polyhedron. Next is convex polyhedron. We will recall the concept of convex polygons. The idea of convex polyhedron is similar. These are convex polyhedron, and these are not convex polyhedron. Regular polyhedron. A polyhedron is said to be regular if its faces are made up of regular polygons and the same number of faces meet at each vertex. Next is a prism. A prism is a polyhedron whose base and top are congruent polygons and whose other faces, that is lateral face, are parallelograms in shape. On the other hand, a pyramid is a polyhedron whose base is a polygons of any number of sides and whose lateral face are triangles with a common vertex. If you join all the corners of a polygon to a point not in its plane, you get a model of pyramid. So these two faces are prism, and these two figures are pyramid. In this figure, the bottom, this face is bottom and this is top. Bottom and top face will be congruent, and this also a prism. Here, this base face and this top face are congruent, and in this case, the top face is pointed, and here also the top face is pointed, and this is the bottom face. So these are prism, and these are pyramid, and these two are prism. So in pyramid, the top will be pointed at a point. Now let's learn one formula for any polyhedron. This F is face, this B represent vertex, and this E represent edge. F plus B minus E will be equal to 2, where F stands for number of faces, B stands for number of vertices, and E stands for number of edges. This relationship is called Eulers Formula. So for solid figure, this is cuboid, this is triangular pyramid, this is triangular prism, this is pyramid with square base, this is prism with square base, and this F represents number of faces, B represents number of vertices, and E represents number of edges. So for cuboid there are 6 faces, there are 8 vertices, and there are 12 edges. So F plus B means this is F, this is B. 6 plus 8 is 14, and E plus 2 is, this is E. 12 plus 2 is 14. And in this triangular pyramid, face is 4, vertices is 4, edge is 6, and F plus B is these two add together 8. Then E plus 2 is 6 plus 2, that is 8. In this triangular prism, this is 5, this is 6, this is 9, 11, 11. Pyramid with square base, and F is B 5, B is 5, E is 8, F plus B is 10, then E plus 2 is also 10. Then prism with square base, face is 5, vertices is 6, E is 8, that is 9, F plus B is 5 plus 6, that is 11, and E plus 2 means 9 plus 2, that is also 11. What do you infer from the last two columns? In this case, do you find F plus B is equal to E plus 2, that is F plus B minus E is equal to 2. This relationship is called Eulers Formula. In fact, this formula is true for any polyhedron. Okay, now let's try exercise 10.3. Question number 1. Can a polyhedron have for its face Roman number 1 triangles, 3 triangles, Roman number 2 4 triangles, Roman number 3 a square, and 4 triangles? So question number 1, answer. We know that a polyhedron is bounded by 4 or more than 4 polygonal faces. Now for this Roman number 1 answer. No, it is not possible that a polyhedron has 3 triangles for its face. Roman number 2, 4 triangles. Yes, 4 triangles can be the face of a polyhedron. Roman number 3, a square and a 4 triangles. Yes, a square and 4 triangles can be the face of a polyhedron. Now question number 2. It is possible to have a polyhedron with any given number of faces. Answer. Possible only if the number of faces are greater than or equal to 4. Now question number 3. Which are prism among the following figure? Roman number 1, a nail. Nail is pointed, so this cannot be a prism. So now this is the answer. We know that a prism is a polyhedron whose base and top are congruent polygons and lateral face are parallelograms. Now Roman 1. No, a nail is not a prism as base is not polygon. Roman number 2, unsharpened pencil. Roman number 2 here. Yes, because base and top are congruent polygons. Now Roman number 3. This is 3. A table weight. No, it is not a prism. Roman number 4, this, a box. Yes, it is a prism because base and top are congruent polygons and lateral face are parallelograms. Now question number 4, Roman number 1. How are prism and cylinders alike? Roman number 2. How are pyramids and cones alike? Now answer Roman number 1. Both have base and top as congruent, face and parallel to each other. Also a prism becomes a cylinder as the number of sides of its base becomes larger and larger. Now Roman number 2. The pyramid and cone are alike because their lateral face meet at a vertex. Also a pyramid becomes a cone as the number of sides of its base becomes larger and larger. Question number 5. Is a square prism same as cube? Explain. No, it can be cuboid also. Now question number 6. Verify Euler's formula for these solids. This is Roman number 1. Solution. Since F plus V is equal to E plus 2 or V plus F plus V minus E is equal to D, this relationship is called Euler's formula, where F is equal to number of faces, V is number of vertices, E is number of edges. Roman number 1. In this figure, number of faces 7, and here in this figure the number of vertices V is 10, and here the number of edges is 15. From Euler's formula, F plus V minus is equal to 2. Now left hand side, F is 7, V is 10, E is 15. 7 and 10 are added together, then we are getting 17 minus 15, then we are getting 2, and this is equal to right hand side, that means this E, these 2. Hence Euler's formula is verified. Now Roman number 2. For this, number of faces 5, number of vertices is 5, number of edges is 8. Then from the Euler's formula, F plus V minus E is equal to 2. Left hand side is equal to V. F is 5, V is also 5, and E is 8. So 5 plus 5 minus 8. 5 plus 5 is 10, minus 8, then we are getting 2, and this is equal to right hand side, this number 2. Hence Euler's formula is verified. Now question number 7. Using Euler's formula, find the unknown face, vertices, edges. This is not given, this is 6, this is 12, this 5, this is not given, this is 9, this is given, and vertices is also given, edges do not give. Now let's try for Roman number 1. From the Euler's formula we know this, F plus V minus E is equal to 2. Roman number 1, for this, F is equal to 2 plus E minus V. This is from Euler's formula. So 2 is here plus, here E means edge, so edge is 12, so 12, and V is 6, so 6. Then 2 plus 12 is 14, minus 6, 14 minus 6 is 8, so number of faces will be 8. Now Roman number 2. For this Roman number 2, we have to find out B. See, vertices B is to find out. So B is equal to 2 plus E minus F. This is from Euler's formula. 2 is here plus, E is 8, so here H is 9, so 9, and this F is face, that is 5, so 5. 2 plus 9 is 11, minus 5 is 6, so B, number of vertices will be 6. Now for this Roman number 3, E is equal to, we have to find out this, that means H. So H is E is equal to F plus V minus 2, this is from Euler's formula. Then F is number of heads, that is 20, and vertices is 12, so V is 12 minus 2, then 20 plus 12 is 32. If we subtract 2, then we are getting 30, so number of H will be 30 here. This question number 7 is over. Next is question number 8. Can a polyhedron have 10 faces, 20 edges, and 15 vertices? To note this, we have to use Euler's formula. Here, solution, no. For any polyhedron, F plus V minus E is equal to 2. Here, F is number of faces, that is 10, and E means number of edges, that is 20, and V means number of vertices, that is 15. Therefore, left hand side, we are taking Euler's formula, F plus V minus E is equal to 2. Here, in this formula, left hand side is F plus V minus E. So, therefore, left hand side, this 10 is F, and B is 15 minus E, that is 20. 10 plus 15 is 25 minus this 20. If we subtract, then we are getting 5. And this 5 is not this number 2. So, hence left hand side, that means this side is not equal to right hand side, that means these 2 and 5 are different. So left hand side is not equal to right hand side. This is not verified by Euler's formula. Therefore, a polyhedron cannot have 10 faces to 20 edges and 15 vertices. Here, this exercise 10.3 is over, and chapter number 10 is also over. And here the syllabus is completed. Okay, for today, all of you, thank you.